In this problem, we're going to find the angle between two different planes. What should hopefully be pretty obvious is that the planes are not parallel. If you can't see this, don't worry, we're going to go over why it's true. The angle between two planes. This is a concept that we did not specifically cover in class, but it's simple because the angle between them is the very same thing as the angle between their normal vectors. So all that we need to do is find the normal vector for the first and the normal vector for the second, and then we can find the angle between those. When I say it should be clear that these are not parallel, well, look at the coefficients. 2x minus 3y plus 4z. Parallel means the same thing for planes as it does for lines in 2 dimensions. What we're looking for here is a pattern where if the second plane contains a multiple of all three of those numbers, then plane 2 will be parallel to this. So like let's take 4z versus 4z in the second one. In order for plane 2 to be parallel to plane 1, what we would need is, since these are the same number, we would need the 6 to also be the same as the -3, which it's not, and the x to be the same as the 2x, which it's not. So the planes are not going to be parallel, and that means that we do have to find the angle between them. So this has a normal vector for plane 1 of, look at the coefficients of the plane. Those are the components of the normal vector. It'll be 2, -3, 4. Okay. And the normal vector for the second plane is 1, 6, 4. Now we're going to reach back into the toolbox to say, how can you determine the angle between not two planes, but two vectors? Because that's what we've reduced the question to. The angle between two vectors can be calculated using the dot product between them. So n1 dot n2 is in principle always equal to n1 magnitude times n2 magnitude times the cosine of the angle between them. So what I'm going to do here is isolate the cosine and say this is equal to n1 dot n2 over the product of the magnitudes. So I do need to find the dot product, and I do need to find the individual magnitudes. I'll do that up here. Magnitude of n1 is square root of 4 plus 9 plus 16. Just squaring all of those numbers. And that's 1329. Okay, so the first normal has a magnitude of square root of 29. The second normal, what is this? Well, this would be square root of 1 plus 36 plus 16. That's 37, 53. So this is square root of 53 right there. So I know that whatever goes on the top, on the bottom, I'm going to have square root of 29 times square root of 53. Now I need to find the dot product. n1 dot n2. This is 2 plus -18 plus 16. 2, I'll just do minus. 2 minus 18 plus 16. 2 minus 18 plus 16. Well, guess what? This is actually going to end up being 0. So in the process of going to investigate what this is going to be, we found out that the dot product is 0. I will put this into what we had. 0 over root 29 times root 53. I'm frankly a little bit glad that we don't need to figure out what root 29 times root 53 is. That would be, inconvenient and messy. So the cosine is 0. At this step, you usually, if you had something other than 0, you would find an inverse cosine of the thing on the other side. However, in this particular case, guess what? When the cosine is 0, you already know what that means. It means that the normal vectors are orthogonal. That means that the angle between them is 90 degrees. And the angle between the normals is the angle between the planes. And so these planes are perpendicular.